Hi, this is Mr. Mitchell with another science video. Today we're going to talk about the kinetic theory of matter and temperature. Go ahead and write down the questions. Here's the video. Kinetic theory of matter. We've already discussed this actually. It's the theory that all particles that make up matter are constantly in motion. Here we have a gas. These molecules are in motion. Here we have a liquid. These molecules are in motion also, not as much as in the gas, but more so than in the solid. And even the solid molecules are vibrating, that they are moving, they are in motion. And all that is called the kinetic theory of matter. And that's something we've discussed for a little while. Consequently, all matter, whether it's solid, liquid, or gas, has kinetic energy. You may remember that kinetic energy is energy of motion, where something's actually being done, as opposed to potential energy, where it has the potential to be being done. So even something like your cell phone may be sitting there, may not be doing anything, or may not appear to be doing anything. All the molecules in it are vibrating. The desk that you're sitting at, the pencil that you're holding, the glasses on your face, if you are wearing glasses on your face. They appear to be doing nothing, but they actually are moving according to the kinetic theory of matter. Gas molecules, of course, move faster and quicker than liquid molecules, which move faster and quicker than solid particles. Now, you may remember that the key to all of this is going to be heat. The more heat you have, the closer to the gas state that you will be. The less heat you have, the closer to the solid state that you will be. So heat drives all of this. More heat, the more you go toward this direction. The more you go toward the other direction, the more cold you have. And that kind of brings up the question of temperature. You know, when we think of temperature, we think of the measure of heat. But heat is the measure of the movement of the particles. So temperature in this fashion is a measure of average kinetic energy. Temperature is a measure of average kinetic energy. So temperature is actually a measure that involves movement, and I'm going to abbreviate kinetic energy, KE. You'll find out that there's actually a formula for kinetic energy in which you use the term KE for kinetic energy. So temperature actually has to do with movement. Now, it's not true that the faster something moves, the hotter it is. Somewhat. The faster a certain particle moves, the hotter it is. If you have this as ice, then the hotter it is, the more close it will be to gas. But when you're comparing different things, different objects have different melting points and have different points of making it evaporate. So when you compare different products, you have different temperatures. So kinetic energy takes into account the specific product, and it also means that it takes into the account the mass. When we get to the kinetic energy formula, mass is part of it. Generally, the heavier solids take more heat to get over to the gaseous stage. So here we have an example here. You can see these cool molecules are moving, but the little things behind them show that you're not moving as fast as these hot molecules. Kind of the vapor trail behind the hot molecules is a lot faster. So temperature measures the average kinetic energy, the average movement in relation to mass. And that's why solids of the same temperature can be hotter than liquids or gases around them. Let's see if I can get to this next one. Here it is. Like the doorknob here. This doorknob may be hotter, and I think if you have like a fire on the other side, then the doorknobs will be hot. This doorknob may be hotter than the air around it. So hot things generally go toward gas, but heavier solids usually take more heat to make it go liquid, to make it go gas. So that's why you can have a hot solid around not as hot gas. And it's also the reason why the mercury does what it does. And that brings up the point of the term thermal expansion. See, all gases, many liquids, and most solids expand when their temperature increases. And that is what the term thermal expansion is. The hotter something is, the more it expands. That's why the red liquid in the thermometer rises under heat. They have just a little bitty narrow tube here. And whenever it gets hotter, this mercury rises up here. And mercury rises at a predictable fashion. Now, not many thermometers really have mercury in it now, but that's kind of the same premise. It rises at a predictable fashion according to the heat. Whenever I was in school, my science teacher, to prove this point of thermal expansion, got out two tongs that look like this. Here we have the tong that has like the solid end to it, and this tong has like a ring end to it. So what the teacher did, she had like a Bunsen burner, which is heats things up, and this end was able to go through the ring. So she put this end through the ring, and then on the other side she lit the Bunsen burner and had a flame over here. So what that did, that heated up this end, and then once it was good and heated, she tried to take this back out, and she couldn't take it back out because it got stuck. So that kind of go to show you that this end actually expanded whenever it heated up. So construction engineers have to take into account this thermal expansion. Steel and concrete also expand under heat. This happens, of course, because particles vibrate more under the heat, and it moves their confines ever so slightly farther apart, just like it did with this end to this tongue right here. Made it just slightly bigger because the confines are moved ever so slightly apart. Does it have more mass when it's heated up? No, it doesn't. It's the same amount of mass. It's just that there's a little more space between the molecules once things are heated up. So for bridges and highways, they have to be put together in segments with slight breaks in them. Now what we have here, I'm sure you've seen something that looks like this. This is called an expansion joint. The expansion joints allow the materials to expand. The road material here is going to get hotter under the heat of the sun. So it's going to expand. So if you have these joints here where when it expands and moves, it's not going to be a problem, then that's a very soundly engineered type highway. If you did not have these joints, that's where you would get a lot of cracks in the road, and you have probably seen roads with cracks in them anyway. Speaking of cracks, concrete is known for getting a lot of cracks in it. And you probably have noticed I've gotten a picture of concrete that has these lines in it. These are grooves that are cut in it because of the thermal expansion of concrete. You get this concrete out in the sun and it's going to expand ever so slightly. And if you didn't have any kind of groove cut in it, then that's where you would get a lot of cracking action, I guess you might say. So thermal expansion is something that's kind of a practical, people had to find practical solutions to overcome thermal expansion. Hey, I hope you've learned a little bit about the kinetic theory of matter and thermal expansion.